Welcome to the section on modeling. In this section, we shall look at a UNET-like architecture which permits us leave from an input image to an output image mapping. You may look at the UNET paper to get the exact UNET architecture. So supposing we have this input right here, that is this image which is of dimension 224 by 224 by 3. We downsample this input image through several layers to obtain this 112 by 112 by C11. That's channel. Supposing after this first step we have channel 1, and then this is the first part of our U, because we're going to create a U-like architecture. Also note that we are going through several layers, not just one layer, before obtaining this output right here. Now what we do next is we have now this other downsampling layers which come after this one to obtain this 56 by 56 by C21 number of channels, and then we have this other layer which is gotten by downsampling this output from this to get this 28 by 28 by C31, and then we have this 14 by 14 by C41, and then finally this 7 by 7 by C41, or rather C51. Now getting to this point and comparing with most convolutional layers, we will get this, flatten it, and then pass through a fully connected layer for some classification. But here, since we are trying to have our outputs, maps, what we'll do is we'll again upsample from this point. So from this point we upsample to get this 14 by 14 by C42. So now by C42, because we are the fourth position, and then we are the second part of our UNET. Now once we get this, we upsample again to this, we upsample again to this. No, we're upsampling through several layers, so it's not just through one layer. And then we upsample to this, and then we may, after this, we may say we want to add some convolutional layers while maintaining this dimensions right here, 112 by 112, and then we get this output mapping where we have 112 by 112 by 3. Now unlike in the input where this 3 represents the RGB channels, where we have the red, green, and blue channels, here we have instead the background, we have the boundaries, and we have the object. In another problem where we may have many objects, or we have several objects in one image, then we will have the background, we will have the boundaries, and we'll have the total number of possible objects in an image. So we'll have, if for example we have a data set where we could have say 3 objects in an image, in that case we shall have 3 plus boundaries plus background, so we shall have 5 instead of 3 here. So this 3 and this 3 don't have a direct relationship. So once we have this output, now we're going to train our model end to end in order to learn this kind of mappings from this input. Now another point we've not yet added into this UNET like network is that given this symmetry between this inputs and the outputs, we could also pass this, that is take this output here and concatenate with this upsampled output, or with this output from the upsampling layers. So concatenating this, that's this one with this, since they have the same dimensions, that the first 2 dimensions are the same, even though the last isn't the same, we shall just add this up. So we will have a concatenated output which is of dimension 14 by 14 by C41 or C41 plus C42. So this will become our new layer right here. Then again we shall take this output and concatenate with this output right here to now obtain this new output. We take this, concatenate with this one to get this new output. We take this output and concatenate with this to get this new output, and then we now train end to end our model. And also from the structure of this architecture, we see exactly why we call it a UNET model. Now, another interesting modification we could do to this network is that instead of building our own layers, which will do this downsampling, we could use a pre-trained model in this first part of our UNET model, such that this pre-trained model extracts already the very important features of this image. And so we use transfer learning efficiently to quickly train our model. Also note that this pre-trained convolutional architecture right here could be a ResNet, mobile net, efficient net, or whatever pre-trained model we have. And also all we need to do is to come to certain positions or get to the parts of this model's architecture where we have this outputs right here, where we have this 112, 56, 28, 14, and then 7. Now also note that we've used 224 as an example here, but any other shape could be chosen. Getting to the code, we should start by looking at the base model. So suppose we have this ResNet 50 base model, which has the input dimensions as this input shape. Then we have, we don't consider the top layers because we not needing this layer, since all we need to do is actually to extract relevant features from our inputs. And then we now go ahead to freeze this base model, and then we could now visualize this base model via this summary. Once we get this output right here, we see we have this input, 0 pattern, this conv layers, which gives us this 112 by 112 output. Then we move now to the 56 by 56 output, then to the 28 by 28, and then to the 14 by 14, and finally to the 7 by 7 output. This model is a 23 million parameter model. Also note that if we modify this input dimension to say 128, run this, we get this output here. So instead of having to work with say 112 as 112, 56, 28, 14, and 7, now we should work with 64, 32, 16, 8, and 4. So that's just how we look at this. And so it means in the upsampling layers, we shall construct them such that we have this intermediate outputs, which can now be concatenated with the inputs or with this outputs from this. Now coming back to the case where we have this input dimension 224, we could have this. Since we shall be using some parts of this model to concatenate it with the parts or its corresponding parts in the outputs, what we shall need is the names of this outputs. So for example, we shall be needing this output right here to concatenate with the output or the right part of the UNET, the upsampling layers. Apart from this, we shall need this. Let's get to the last point. That's this one here. So we shall also need this, and then we shall need this 28. Yeah, we shall need this, and then we shall need this one again, and finally we just get this output right here. So here are the names of the layers which we shall be needing, so that we could take this output and then concatenate with the right hand side of our UNET model. So that said, we could take this off, and we have this. So here we have this conv1 relu. If we take, let's start from this last one. We have this conv5 block 3 out. See, it matches up with this. If we go up to the place, okay, so we have this conv4 6 block. See, it matches with this. And right to the top, we have this conv1 relu, which is this. So basically what we're doing is we're extracting this output from our ResNet model. And the way we do this is by come into this base model, which we've defined right here, and get in the layers. So we have the base model dot get layer, and we specify the layer name, where layer name comes from this. So we have this one, this, and this. So this means that if we were to use, say, a mobile net version 2 or any other model in the place of this ResNet 50 model, what we'll have to do is first get the output or get the summary of the model, and then select the exact positions or the exact layers whose outputs will be used in concatenating with the right hand side of our UNET model. So that's what we just did. We have this. See, we explicitly write this because these are the names we're getting from this. So once we have this one, now we now return this model. And also note that this is why it's also important for us to always put these names to our layers and models, so that they could be referenced like this very easily. Because if these names hadn't been there, we'll have some names, but they wouldn't be as descriptive as the names we have here. So that said, we have this model we return. We're taking the base model inputs, and then we output this from the model, or from this selected model outputs we're getting here. Now we rerun this again, and everything works just fine. Now the next thing we'll be doing is we'll be defining the right hand side of our model. So we have this inputs. We then go ahead and resize this inputs. Let's modify this. And once we resize this inputs, we now pass through this model base here. We get the base model, which is this function right here. So with this, we get the base model, and then take into consideration the fact that we are also getting this outputs, or the selected outputs at these positions where we have this output for which the shape is 112, the output for which the shape is 56 by 56 by a certain number of channels, the output for which the shape is 28, output for which the shape is 14, and then the final output which has a shape of 7. So that's it. So once we have this, now we now go through this upsample layers. We shall define the upsample layers subsequently. So let's just take this and put right here. Okay, so we have this upsample layer, which takes in a certain number of filters. We shall get into details of this shortly. What this does is it first takes in this output, which has dimension 7 by 7 by a certain number of channels. In this case, it's 2048. So we take this and then pass it through an upsampling layer. It gives us an output X. Now this output X is of dimension 14 by 14 by a certain number of channels. This output is concatenated with this output from our base model. Then once this concatenation is done, we again upsample this. So we again upsample this, and then we concatenate, because this upsampled X here will have dimension 28 by 28 by a certain number of channels. We concatenate it with this output from the base model, and then we obtain an output X again. We upsample it, and then we concatenate again with this X56. We upsample, we concatenate with the X112, and now since our output needs a certain number of channels, that is specifically 3 number of channels, we have this conv layers where we make sure the pattern is the same, so we don't change the first 2 dimensions of our output. So we get this output now, which is of dimension 112 by 112 by 3. Also note that we could configure our network such that our output is of dimension 224 by 224 by 224, or even be of dimension 448 by 448 by 3. So that's it. We could also have this kinds of outputs. Also, after concatenating this input, or this left side with the right side of the UNET, we could include some conv layers, which could permit us learn more information from this output, which is a resultant of the concatenation of the left side with the right side. So we could define this conv layers, which take a number of filters, and then have this. So it takes in this x and then has parameters number of filters. So we could just have this, right, this, and there we go. Now all we're left to do is to define this upsample and then the conv layers. Firstly, for the upsample layers, we have this conv 2D transpose layer, which has number of filters which has been defined, and then a filter size of 1, number of strikes of 2, so that we could upsample by a factor of 2, and then this ReLU activation, and then we also include this batch norm. So basically what we do is once we pass an x, it goes through the conv 2D transpose, and then it goes now through the batch norm layer. So this is our upsampling layer. And then for the conv layers, we simply have this. What this takes is the number of filters as we have defined already. Then we have this first conv 2D layer, which has this number of filters by 2, which 3 by 3, pattern the same to ensure that we don't modify the dimensions. And then we have this conv 2D again, followed by this batch norm. So basically what we do is we have the conv 1 batch norm, conv 2 batch norm. So we could run this now and then run this, and there we go. We have this model which is close to 34 million parameters, 10 million trainable, and the non-trainables are 23 million. Note that given the fact that we have only about 7,000 images in our data set, we'll need to do very heavy data augmentation to make sure that our model doesn't overfit on this data set, since this model has so many parameters. So that said, our model is ready for training. See you on the next section.